Welcome you all to the EPG Pathashala program on the course Compiler Design. This is the third module, and the objectives of this module are to understand the happenings in the lexical phase, to know how to define patterns using regular expressions. So, that is the fundamental objective of this particular module. So, last class we looked upon the phases of the compiler, the 7 phases. The 7 phases which includes a symbol table also, the 6 phases along with the symbol table and also error handler. So, today we will brief on the first phase of the compiler, lexical phase, what it does, how it does, and what are the various methodologies, how to do it faster, that is more important than what it does or how it does. Major things that happens in the lexical phase are the scanning and the lexical analysis. Scanning basically is the first part, which does deletion of comments, compaction of consecutive white space characters into one. In the lexical analysis phase, which is the more complex portion, where it produces, the lexical phase essentially produces tokens based on the output of the scanner. So, the input to the lexical analysis phase is typically a program which is a text file or a .c file or a .pascal or a .java file, and the output will basically be a sequence of tokens. So, after this part, the input source language is basically completely broken into pieces, where each will have a corresponding token associated with it. So, what it does is it reads an input file, it identifies the language keywords and the standard identifiers. So, the first input is a text file and output will be a sequence of tokens. Now, what it does as a processing is it reads the input file, it identifies the language keywords and standard identifiers. This also includes the hash include files and the macros. It counts also the line numbers, it removes white spaces, it reports illegal symbols, and it forms a symbol table. So, these are the basic actions that is performed as part of the lexical phase. The lexical analyzer typically, last class we saw about 6 phases of the compiler. So, will I have 6 passes for the 6 phases was the question posed last week in the earlier modules, where we talked about combining all the first 4 phases into a single pass and the remaining could be as separate pass. Now, will the lexical analyzer be a pre-processing step other than the parsing and the intermediate code generation? The answer is definitely no. Normally, you have to basically combine the lexical analysis phase along with the syntax analysis phase. So, but the problem is if you have it together, it is going to be resulting in a complex design. But if you have it as a separate phase, it eases the design and it improves efficiency and portability. So, what we normally do is we normally incorporate the syntax phase along with the lexical phase, and then after that it tokenizes and it validates every statement. That is what is given to the next, which is the intermediate code generation phase. So, typically the lexical analyzer is combined with the syntax analyzer phase. So, this is essentially what I was talking about just now. So, you have the lexical analyzer which is going to issue a token to the parser, it is going to give a token to the parser. The parser, which is the second phase of the compiler, is the syntactic phase of the compiler, requests for a new token by talking to the lexical analyzer, saying that okay, give me the next token, and the lexical analyzer on the other hand issues a new token to the parser. Both will interact with the symbol table in the process of token exchange. So, with that we are in a process of combining the syntax phase and the lexical phase. This combination will basically simplifies the syntax analysis in terms of language definition. It also enhances modularity and portability, it enhances reusability, and it will be efficient if I do it in this particular fashion. Let us go through this phase in a more elaborate manner, where we are going to define some terminologies that is going to be used as part of the lexical phase. The first one is being a lexeme. Lexeme can be thought of as a particular instance of a token or an instant of a token, where lexeme is nothing but a sequence of characters. Token, on the other hand, is a group of characters having a collective meaning, that is, it is a name given to the lexeme, that is what you can generally say it. So, lexeme is a sequence of characters, while on the other hand token basically means a name given to a lexeme. So, but we normally try to use these two interchangeably, but essentially lexeme is what this from the source program you go through a sequence of characters and then you say that this corresponds to a lexeme, and what name you give it to it is called as the token. For example, I am going to give a token called as identifier and for the lexeme which is pi. Now, where will I get the lexeme from? From the source file. So, the source file has got this particular keyword basically called as the pi. So, the pi is going to be the keyword corresponding to available in the source file. Source program, I have this keyword called as pi, and using that I can basically say that this corresponds to the token identifier. Now, what is this pattern? The pattern is a rule that describes how a token should be formed, or I can even say how a lexeme should be formed. Now, I already said the terminology lexeme and the token keeps repeating, normally is used interchangeably. So, what is that we are trying to look at is pattern is how do I define a lexeme. Now, after defining a lexeme using a particular pattern, I will be associating a corresponding token with it. Okay. So, pattern is a rule that describes how a token can be formed. Now, the basic component of this particular phase of the compiler is to define patterns for every possible lexeme, and then for this pattern what token will you give it is what we are trying to look at this particular phase of the compiler. Can say what issues can basically happen in the lexical analyzer. Now, the problem is how do I identify tokens? Okay. They are normally given as patterns in terms of either a regular expression or as a non-deterministic finite automata or as a deterministic finite automata. And the second issue is normally how to recognize the tokens giving a token specification and how to implement the next token routine. So, this is already solved where you have already integrated the first two phases of the compiler, and the syntax phase and the lexical phase talk to each other in terms of token exchange. So, using the tokens given by the lexical phase, the parser will normally check for the correctness of every statement of the source code. So, again coming back to this, given a set of tokens and a token name, you will define a regular expression defining the pattern for a particular lexeme, and you will also have the input string, and you partition the string into tokens and associate a corresponding identifier. Now, there will be an ambiguity because we have already, if you remember, we have already talked about removing the white spaces as part of your lexical phase. So, lexical phase we already said it is combination of scanning followed by analysis. So, in the scanning itself we have basically removed all the white spaces, and if I have removed the white spaces, what is the problem? I will have sequence of characters occurring. Okay. In that case, how will I identify what is my correct lexeme? So, normally what happens is the longest matching token is chosen. Okay. So, the longest matching token is chosen based upon a given pattern, and supposing if I have two equivalent tokens, the one which is coming first is chosen as your corresponding token. So, this is how you resolve ambiguity in the case of lexical analysis. So, for example, we have a set of token, their lexeme and the corresponding description. A token is if, okay, and the description is the sequence of character I followed by f, and the sample lexeme is the same word if itself. Okay. This can be given a token as also keyword, if is a keyword. Okay. Again else can be a token or lexeme. The identifier it basically gets is called as the keyword again, and the characters E followed by L followed by S followed by E is going to be the description of the lexeme else. Okay. And the next one is the comparison operator, where I can have a less than or a greater than or a less than or equal to or a greater than or equal to or a double equal to or a not equal to, and in that case the sample lexeme will be less than or equal to, you can get any one of these. The next one is identifier standing for that is your token identifier. It is represented in shorthand as ID typically, and the description is letter followed by letters and digits. So, you can have an alphabet followed by that you can have an alphanumeric character, and sample lexemes are P followed by I, you can have a capital letter in the beginning, or you can have a small letter in the beginning, or you can have a small letter followed by 1, 2, 3, which is a number basically. And the next token which we normally encounter is the number, which is corresponding to any numeric constant. So, 3.14, it could be a floating point value or it could be an integer value, which is 3.14 or 9.08, etc. And we say something as a literal, which is available within double quotes. Example, segmentation fault. So, if I have something within double quotes, say for example, your printf statement in a C programming language will have the value is or hello world. So, within double quotes whatever you have, that is called as the literal. This is the example from Aho Sethi Ullman textbook. After getting the token, we normally have an attribute associated to a particular token, okay, which the attribute is typically a pointer to the symbol table entry in which the information about the token is being present. Example, let us take this equation, E is equal to m into c squared. Okay, Einstein's theory of relativity, E is equal to mc squared. So, what will it happen is the lexical phase will try to find out that the first character is going to be a E. Okay. So, it will look at the first character as being a E, and then it will say that is an identifier, okay, that is the longest matching string, because next you have an equal to is not part of your identifier. So, E is the identifier and the attribute it has is pointer to the symbol table entry for E. So, where E is available in the symbol table, it is going to have a pointer to the symbol table entry. The next one is an equal to, again equal to is your longest matching pattern here, equal to followed by m does not make any sense. So, equal to is the longest matching pattern. So, the corresponding attribute it has is assignment operator, and in that case there is no attribute. So, simply the token is available as assignment operator. The next one is again mc squared, right. E is equal to mc is followed by multiplication symbol followed by a c followed by double star and a 2. So, m again is going to be an identifier which again has the pointer to the symbol table entry, and the next one is a multiplication operator which is again star, and then id, next one is again c which is id, which is again a pointer to the symbol table entry, similar to what we had for e, m and c, all these are same. And then you have an exponentiation operator. As you could see, it is trying to find out the longest matching pattern. So, star for multiplication operator, if you could see, that has got 1 star, whereas exponentiation has got a double star. So, it is trying to find the longest matching token and identifies the corresponding attribute and associates a token with it. Okay. So, double star will be fetched here, where it is identifying that as an exponentiation operator, and the last one has a numeric constant as 2. So, the token is num and the corresponding attribute is integer value 2. So, token and attribute, token is the name given to a lexeme. So, what is my lexeme here? E is a lexeme, equal to is a lexeme, m is a lexeme, star is a lexeme, c is a lexeme, double star is a lexeme and 2 is a lexeme. What is the token given to it? For E, m and c it is going to be identifier, for equal to is assignment operator, for star it is multiplication operator, for double star it is exponentiation operator. And what is the attribute? For the operators you do not have to have an attribute, for others you have to have what do you mean by num, because number, a numeric constant could mean 1 or 2 or 3 or whatever it is. So, in that case the attribute is going to be definitely necessary. For the other cases, for the identifiers, typically it is going to be pointed to the symbol table entry. Some examples we have here, because we already said that this pattern is going to be given as a regular expression. So, this module will talk about regular expressions and the difficulties in having a regular expression here as compared to other ways of pattern matching. So, 3 things are mandatory. One is associating a lexeme, giving a token to the lexeme, and the token will basically have a corresponding attribute, and defining patterns for explaining the lexeme and the corresponding token. So, we are going to resort to regular expressions for defining patterns. Let us take this example. I have a sequence of regular expressions and basic patterns and the corresponding interpretation of what it basically does. The basic pattern is x here, for example say, it simply says the character x, okay, and when I have a hyphen, it simply says any character except new line. So, hyphen could mean any character basically, and then the one within xyz, within square brackets x, y, z, it means any of the characters x or y or z, any one, okay, of the characters x, y, z. And then r question mark, it says an optional r, which means that you can either have an r once or none. Okay. So, 1 or 0 occurrence of r is given by a question mark, and the next one is r star. Okay. This r star is what we have to focus on, because that is necessary aspect which is used to form corresponding regular expressions. I will explain this towards the end of this module. R star basically says 0 or more occurrences of r, and r plus says 1 or more occurrences of r, and r1 r2 says r1 followed by r2, and r1 or r2 says either r1 or r2, and r says within parenthesis says simply r by itself. Now, this r star, what it does basically is, r star essentially says union of I equal to 0 to infinity L par I, or rather r par I. Now, what is this r par I 0 to infinity? So, it is going to be r 0 comma r 1 comma r 2 etcetera up to r infinity. Okay, that is your complete set. If I say that is my complete set, r 0 basically tells you a length of string 0 from r, which is epsilon. Okay. One occurrence of r, okay, whatever is r, one occurrence of r is r1, r2 means 2 occurrences of r, which is r2, r3 means 3 occurrences of r. Now, 2 occurrences of r means what? For example, if my r is going to be a character a, then one occurrence of r is simply a, 2 occurrences of r will be a followed by a, 3 occurrences of r will be a followed by a followed by a, and so on. Supposing r itself is ab, okay, in that case one occurrence of r will be ab, 2 occurrences of r will be ab followed by ab, 3 occurrences will be ab, ab, ab. So, it is not length, it is just one occurrence, 2 occurrence, 3 occurrence, or whatever it is. Now, using this star operator, you can form a set which is going to have strings of infinite number. So, when I have infinity, you have star, which means 0 or more occurrences, which means that no occurrence of r, 1 occurrence of r, 2 occurrence of r, etcetera up to any combination. So, what will be the length of, what will be the number of elements in this set? It is going to be definitely infinite, okay, which is going to start from epsilon, which is no occurrence of r, and then others. Okay. Similarly, if I have plus, r plus is 1 occurrence of r, 2 occurrences of r, etcetera. That is, this alone is not being present. Okay. And I can also form my r, here I have got a followed by b, which is r1 followed by r2. I can also have my r as a or b. Okay. This plus is basically used to indicate the or operator. Now, I can also say r star, which is a plus b the whole star. Okay. If I say a plus b the whole star, it is going to be what? A plus a comma b, plus also means r, right. So, a comma b, that is one occurrence of r, r2 means what? 2 occurrences of r, which is a plus b followed by a plus b. So, which how many strings will I get here? I will get 4 strings, which is a, ab, ba, comma bb. So, this is 2 occurrences of r. 3 will be this followed by a plus b, which will be 8 combinations of length 3 each. Okay. So, this is how you normally form strings of infinite cardinality, I mean strings such that the number of elements will be of infinite cardinality. So, moving on with our talk here. So, let us look at some more examples. So, regular expressions, I can use these 3 operators, the fundamental operators of star, the plus and the dot. Dot means concatenation operator, and this is nothing but the or operator. So, using that I can basically form any number of strings. Now, okay, we know what is a regular expression. It is used to define patterns, that is known to us, but what is it used for here? So, basically your identifiers in C language, that is your variables in C language, can be of the form, it can be a letter followed by letter or digit the whole star. That is, the first character is a or a b or a c, etcetera up to small z, capital A to small z, capital A to capital Z, or small a to small z. The first character is letter. After that, I can have an option of either a letter or a digit combination. So, this sentence in English or this understanding in English of my definition of variable will be translated into what is called as a regular expression of this particular nature, which is letter followed by letter or digit the whole star. Okay. So, where here the star has the highest precedence, that is this operator is called as the clean closure operator, it has the highest precedence, followed by the dot. Dot is called as the concatenation operator that has the next precedence, followed by the OR operator which has got the least precedence among all the three. Okay. So, with that we will move on to some properties. If L of R is a language for regular expression R, L of S again is a regular expressions language, then L of R union L of S is also going to be a regular expression. Similarly, if L of R dot L of S will also be regular expression if L of R and L of S will be regular expressions. Now, what is L of R? L of R is the language corresponding to the regular expression R. L of S is what? Is a language corresponding to the regular expression S. How will I form the language? Using the regular expression operators in terms of star, dot or OR operator. Okay. So, example I have already given you these two examples, L1 is equal to A star I just now explained, and L2 is equal to A or B also I just now explained. A or B means only two strings, one is A, other one is B. Okay. Now, for defining the variables in C, we normally go for what is called as a regular definition, which is nothing but the regular expression in a consolidated form. Okay. So, we can call that as names given to the regular expressions that can be thought of as regular definitions. Okay. So, for example, it will be D1 produces R1, D2 produces R2, D3 produces R3 etc., where each DI is a symbol not in the input alphabet. Okay. Example I have here, letter produces A or okay, the arrow basically says produces. Okay. Letter produces A or B or C etc. up to small z, that is A to small z. Digit produces 0 or 1 or 2 or 3 etc. up to 9. What does it basically mean? If I am using letter, I could replace that with either a or a B, or any one could be replaced in place of this letter. Similarly, when I say digit, any one could be replaced in terms of digit. Now, identifier is my definition, which is letter followed by letter or digit the whole star, which is letter followed by letter or digit the whole star. Now, supposing I want to write this without using the regular definition, how will I write it? It will be A to Z followed by A to Z 0 to 9 the whole star. I could also use underscore here. This is a Pascal definition basically, where it does not it will not include underscore as one of the operators. So, rather than writing it like this, we have basically said we are giving a new name to it and then calling it as a regular definition. One more example here will be for representing floating point number, where I have defined what is a digit. I have also defined how digits will normally look like. Digits is more than one digit. Okay. So, which is digit followed by digit star. Digit star means what? 0 or more occurrences of digits. So, I can have this optional and then digit star. I will have an optional fraction 9.08. After the point, you may have some number or not, does not matter. Therefore, epsilon is available here. I can also have an optional exponent. Exponent means of supposing you have in the exponent mantis-R representation, you have 9 followed by e followed by 10 power plus 0 minus 2, okay, plus minus 2 or minus 0 2, something you will have, right. So, that is nothing but exponentiation representation, where you can have an optional exponent part, whereas it is going to be e followed by plus or minus followed by epsilon followed by digits or epsilon. I could either have like this or I need not have it. That is why we have an epsilon in place of these 2 points. Finally, number will be digits followed by optional fraction followed by optional exponent. Okay. So, digits will be what? This will also take care of your integer number and as well as floating point number. So, integer will be from here, where this could be any number of digits followed by an optional fraction. Optional fraction will be dot followed by digits or epsilon, and optional exponent will be either a e followed by something. This is one more example of where statement produces if expression then statement. I have defined expression as term relop term. Relop means relational operator, where term can be ID or number. ID could be this we have already defined. Relop will be less than or greater than, less than or equal to, or greater than or equal to, double equal to or not equal to, and number produces digits. If I go in the reverse, I can basically substitute this with whatever I want and get my actual string. Now, normally we do not, we could specify patterns using regular expression, but what normally happens is sometimes it is very hard to define a regular expression for some languages. So, in that case what we normally do is we define it what is called as a automata, which could be a definite automata, deterministic finite automata, or it could be a non-deterministic finite automata, calling it as NFA or DFA. Now, there are variations. You have an NFA with epsilon, without epsilon. You could define any one of these three, okay, and then you have algorithms to convert this back to regular expression, okay, and that could be used for your pattern specification. So, either your pattern should be in terms of your regular expression, or it should be in terms of an automata. An automata will typically be a DFA or an NFA, as I already said. So, where you can also specify a partial automata with regular expressions on the edges. You need not specify all the states, different actions could be specified at different states. This will be part of the next module anyway. So, I will just give you some example here, where you create a non-deterministic automata from every regular expression. You can merge all the automata using epsilon moves, and then you can construct a DFA or deterministic finite automata, and you can minimize the automata so that it is going to be faster in string matching. So, we have some definitions here. Anyway, I will talk about this in the next module also. So, where a deterministic finite automata is going to be really fast in string matching, because there exactly exists one path from the start state to the final state for every valid string, and if the string is invalid, you will not have a path at all. On the other hand, for a non-deterministic finite automata, it will take a little more time for string matching, because there will be multiple paths, and out of all the available paths, even if one path could take you from the start state to the final state, you will call that as a valid string. A non-deterministic finite automata with epsilon moves, this is going to be even slower, because you could also go from one state to the other state without consuming input symbol at all. Okay, so, this is one example. I will anyway discuss about this example in the next module when I talk about pattern matching with DFA and NFA. So, this is just a pattern for specifying if. So, I followed by f, the final state corresponds to the token if. You will also return the attribute for this particular token, which is nothing but a keyword. Okay. So, this is what you normally represent. On summarizing, we have talked about here the work involved in lexical phase in terms of scanning and analysis, tokenization, lexeme formation, and defining patterns for the lexemes. So, we also looked at some regular expression for defining variables in C and defining number in C, numeric constants in C. But constructing a regular expression is difficult, therefore, we normally would like to go for a DFA, NFA or an NFA with epsilon transitions. That will be discussed in the next module.